Я понял. О, Боря, привет, Боря.
Okay, so let us start our afternoon session. And the first speaker is Evgeny Kuznetsov with the talk Breaking of Sleeping Flows in the Boundary Layer. Please.
Okay. First of all, let me congratulate Andrei again with his remarkable anniversary, and I wish him health and health once more. And so my talk will be devoted to sleeping flow. So I would like to remind you some basic question. When you consider fluids and some rigid boundary, in such a case, you have two kinds of boundary conditions. One when you have a viscous case. In viscous case, the velocity vanishes, complete components, but when you consider boundary sleep boundary conditions, then in such a case, the only normal component of velocity is equal to 0. And but as far as tangent component velocity, it somehow remains more or less free. And it turns out in such a case, you have a new possibility for breaking of such flows. So flows which you have just on the boundary. And it's a main topic of my talk. My God, what happens? I cannot. So there will be some long introduction and motivation, and probably the question will be concerned finite time singularity, so blow up, and it's still open question in spite of progress in both numerical and analytical studies. And for instance, in our numerical and analytical investigations together with Agafontsov and Mylibov, which publish a lot of papers, for periodic boxes, we have observed formation of high vorticity structure of the pancake type. And the most important point that we observe only exponential growth of vorticity without any tendency to blow up. And such increasing is connected with the vorticity compressibility. And probably it's one of the crucial point in this. So this means that at least in our numerics, we didn't find any blow up behavior. But if you consider the presence of rigid boundaries, recent findings, both analytical and numerical, demonstrate blow-up behavior. For instance, the paper by Kishelyov and Zlatos prove blow-up existence if the boundary is not smooth. And this means that you have, I don't know, some cones or something like that, and just a cones provides you appearance of singular behavior. So if you look at, say, Landau-Lifshitz book, then you can find that even if for stationary case, you have in a cone, for instance, then you can find immediately that behavior has a singular. And therefore, it's interesting point. For three-dimensional situation, but not axisymmetrical flows, there were very interesting numerical experiments performed by Liu and Hao, and they demonstrated that inside the cylinder with a constant radius, they observe appearance of collapse just on the boundary. And it was a challenge why boundaries play important role in formation of singularities. And later two guys, this is written here, and they investigated this question more or less analytically, but they considered not the flow inside the linear, but outside. And secondly, they found that if this boundary has some, I don't know, angle or something like that, appearance of singularity takes place just in this corner. So in some sense, it correlates with the Kishelyov and Zlatos results. So in this paper, we show that the flat boundary itself introduce some element of compressibility into the flow and can be considered as a reason of singularity for formation of the boundary. And we consider two-dimensional, three-dimensional Biscuit-Prandtl equation, which describes dynamics of boundary layer, and demonstrate the singularity is formed of the vorticity for velocity gradient on the wall. And this process is nothing more as a breaking. Usual breaking, like I don't know, for in a famous Riemann simple waves. It's necessary to say that before us there were a few papers in 1985. So there was a paper by Ian Anderson, and then there was some which demonstrated some for some initial conditions and some appearance of blow up behavior for Prandtl equations. And before it was a very exciting numerical simulation performed by Donovan and Shen. And recently enough, in 2003, Honk and Hunter investigated this problem for both viscous and Biscuit-Prandtl equation for zero pressure gradient. And in particular, in the Biscuit case, they noticed that singularity can appear just on the boundary, so on the ball. Now let me write down the equation for Prandtl. And so this equation is written here for u. It's a longitudinal component of velocity, and according to Prandtl approximations, this velocity is much larger than the normal component of velocity. This means that boundary layer has a very small thickness in comparison with longitudinal size. And in such a case, P standard here at the pressure doesn't depend on time x and y, and P is a function of x, and it is given and it is defined asymptotically at y tends to 0. Y is equal to 0. It's just our boundary on the ball. So it's initial conditions, etc., etc., and so you can see something very simple. And so what I would like to pay your attention, I would like to pay your attention that if, for instance, P is equal to 0 or constant, then and on the boundary, as I told, V must be equal to 0. Then if when you choose both terms, then you recognize that remains on the boundary is nothing more as a Hopf equation. And if you have a Hopf equation, then you will get immediately appearance of singularity in a finite time. So it's not a question, it's just simple exercise now. But however, it turns out that there exists another way how to solve this equation for the whole region, which we have here. First of all, if we return to our equation, then if Px equals 0, then you can see that U standing here is nothing more as a Lagrangian quantity. So it moves together with fluid. And this means that let's consider now some Lagrangian quantity which moves to advected by the fluid. And then you have such type of equation. Let's assume that you have such a solution n as a function of x and y and t. And then consider the inverse function y as a function of x and time. And it turns out that such type of transformation is well known for Prandtl equation and it was introduced by Crocker in 1939. Oh, it's a very interesting point. Unfortunately, I already discovered Crocker transformation, but however, it's a slightly different way how I introduce such type of equations and how this can be applied for these equations. So what we have? We have indeed some Legendre transformation because of y is a function of n, x, and time, but it's not complete like in Hadograph transformation. So it's a crucial point. And then after that, it's possible to perform the usual exercises to recalculate corresponding derivatives, and it results to the following interesting equation. If you introduce the stream function, then it turns out that these equations comes to the linear one, so y and psi, so you have a linear relations. And if you have a such type of relation, then you can introduce generated function, which is written here, and it turns out that you have a linear equation. So sorry, I can show you. Ah, my God. No, it's so how to change it? My God. So it turns out that for theta, for generated functions, you have linear equations. But if we come back to in Biscuit-Prandtl equation, then it turns out U in such a case will be described by such type of variables, and for these derivatives with respect to U, you have a linear equation which can be solved immediately. It's not a question, and it gives the integration with respect to U. It'll give you the solution, and this solution can be found. Unfortunately, I cannot move. I don't know what's it. Oh my God, I don't know how to. So theta in such a case will be found by a simple integration with respect to U, and after that you can find general solution for this problem. And boundary conditions. For boundary conditions at y, as I told, px is equal to 0, and this Prandtl equation is nothing more than the Hopf equation. And Hopf equation can be solved immediately using the method of characteristics, which gives immediately appearance of a singular behavior as a function of time in some point where the corresponding derivative with respect to U0, it's a time t star, it's Wilhelm fact, and then after that you have a solution. So solution for y and psi is written here. Unfortunately, I cannot show you this formula which is written here. I don't know, maybe you see, but unfortunately I don't see. And after that you have a solution. For instance, the solution can be found also if the gradient px is a constant, and the solution for y and psi is written here. So you have a Hopf equation again, by px here is a constant, and it can be solved also using method characteristics, and gives also blow-up solution when initially. It's interesting that if you perform the Crocker transformations for equation for omega, in the Prandtl approximation, it turns out that omega is nothing more than derivative with respect to y, then you have a such type of equation. And as a result of Crocker transformation, you have a linear equations where all coefficients standard here doesn't depend on time and can be solved immediately. And it follows immediately that as a boundary, you have a Hopf type equations for px. Px in here, it's arbitrary function of x. Of course, it can be solved, and it gives you your Newton equations for characteristics. And with a pressure which depends on coordinates x, and after that you can analyze what it necessary to do. Now let me now consider another very interesting three-dimensional in Biscuit-Prandtl equations. So the three-dimensional in Biscuit-Prandtl equation has the following form. It's written here. U standing here, it's a parallel component of velocity. So you have the usual term, plus derivative with respect to z. Z here, it's a normal component. Z, it's a vertical coordinate to the wall. And P standing here, again, is a function of R only. R here, it's x and y. And the gradient here is standard with respect to x and y only. So again, you can see very interesting phenomena as a boundary. If the velocity v is equal to 0 and p standard here for simplicity is equal to 0, then you get such type of equation ut plus u gradient u. So you have a gather dynamics for gas with zero pressure. And this equation was analyzed first time, it seemed to me, by Zildovich when he introduced his famous pancake theory of formation of proto-galaxies. And they have also something, pancake structure. And in fact, it follows from just this equation, if velocity is equal to 0 and gradient p is equal to 0 also, and in such a case, you can solve this equation up to the end. And in fact, what is the main point in my talk? The main point in my talk is that as the velocity, the boundary velocity, we arrive at the two-dimensional Hopf equation, which can be solved by method of characteristics. It's not a question, but here there exist some tricks which I suggested, I don't know, many years ago, in 2003, it seems to me, and published in Physica D, and I can show how it's possible to solve these equations more or less exactly. So let's consider for simplicity the case when the pressure is a constant simply. And then let's introduce the velocity gradient, which is written here, u capital ij. It's a derivative of the velocity components with the x, j. And then it follows immediately. Then if you consider our equations and differentiate with respect to coordinates, this equation p is equal constant and it's equal 0, then it turns out that you arrive very interesting and simple equations. DDD here, it's a derivative for how to solve. So the long derivative, and so in method of characteristics, it's just material derivative ddt or Lagrangian derivative. And then you can see such type of equation. You here it's a matrix. In our case, it's a matrix 2 by 2. And this solution of this equation can be written in such a way. So you can recognize and you can substitute and verify that it's just the equation which is written here. So what is it U0 of A? U0 of A and A standing here are the initial values of matrix U and position of fluid particles. So you can, oh my God, again, I'm very sorry, I don't know how to proceed it. So how to analyze this solution? This solution can be analyzed as follows. Let's expand the matrix U0 as a function of A through the projections of this matrix, and then you will get. I'm very sorry. U will be equal to sum. Lambda alpha is an eigenvalue for this matrix. P alpha is a projections, and then it's necessary to divide by 1 plus lambda E multiplied by T in denominator. I'm very sorry because of it's some technical question. I don't know how to solve it. And then after that, I can immediately can analyze everything what it is. First of all, it seems that you have a dominator, and this dominator can vanish, and it's just nothing more as a breaking time. In some point, it's necessary to consider such a quantity minimum value with respect to all alpha. So you have two alphas here, and A as a function of A, and then after that it's necessary to find minimum, and after that you can get immediately that the main contributions in a single point comes from the minimum value, minimum eigenvalue lambda alpha. And near this point, it's more or less evident, U will be proportional to T1 minus T minus 1. So you have the same behavior like in one-dimensional Hopf equation. So you have a singular behavior. But the most important point is that this gives simultaneous singularities for both symmetrical part is a stress tensor and anti-symmetrical part. It's a Vasicity. So this means that if, for instance, for two-dimensional flows, when you have a usual Hopf equation, in such a case, you have a singularity only for stress tensor, but here you have not only singularity for stress tensor, but also for Vaticity. And from my point of view, it's a very important result, because I believe that it can explain the appearance of separation of vortices, just the problem with I don't know, with the usual airplane. So you remember that lifting force appears according to the Zhukovsky theorem due to separation of vortex. And I believe that appearance of such type of singularity can provide such separation. And such separation, from my point of view, must be somehow connected with the appearance of singular behavior near the wall. So I have time.
You can
to
finish
and
what
so,
you're doing is, excuse me, do you consider what you're doing could be applied to separation of water in river sources or something like that? In a real prop,
yes, it's a real property. Of course, it's the most important point from my point of view is the following: that slipping flow itself has some compressibility property, and this compressibility property provides breaking phenomenon. Say, let's take just not Brandt's equations. Say Euler equations, and near the wall, so on the surface of the wall. In such a case, normal component of velocity vanishes, and therefore the main derivative in such a case will define only tangent component of velocity. Of course, it will be equal minus gradient pressure, but if we assume that it's not essential, then you will get that this part gives you something which is nothing more as a Hopf equation. And in such a case, you can expect formation of singular behavior. But of course, in real Euler equations, P is a functional. It doesn't depend on X like in a Brandt approximation. So it's necessary to consider. But however, I believe that this fact must be very essential in order to provide the appearance of singularity. I believe that a numerical experiment, which I mentioned before, by Hall and Low, they demonstrated, in fact, the appearance of singularity on the wall in cylinder for three-dimensional swirl flow. So when you have all three components, radial, azimuthal, and z component. So it follows immediately that on the wall, the wall of cylinder, the normal component is equal to 0, exactly. Then in such a case, you can see that azimuthal component of velocity also vanishes because of you have only derivative with respect to z. It's a coordinates along cylinder, and then you recognize that all this guy on the boundary somehow gives you some understanding why you have to expect formation of singularity in such a case. It means that in such a case you will get appearance of singularity due to breaking. Of course, pressure standard here. It's a separate question, but I believe that the main reason is connected with the slipping flow. Slipping flow is the main reason of appearance of singularity. So about conclusion. So what we demonstrated? We demonstrated for the two-dimensional in Biscuit-Prandtl equation, we have developed the mixed Lagrangian description based on the Crocker transformation. So why I say about mixed Lagrangian description? Because of when the pressure is constant, then the longitudinal velocity u is nothing more as a Lagrangian quantity. But the coordinates along x, it's a Eulerian. So you have mixed Lagrangian description, and it's a very important point. And I believe that application of Crocker transformation can be applied not only to this problem, I mean two-dimensional Biscuit-Prandtl equation, but probably maybe for another fluid problems. The next. Application of this description to the Biscuit-Prandtl equation allows to construct a general solution written in the implicit form. So unfortunately, formula was, I don't know, but the same situation takes place for the usual, I don't know, solution for.
Right now, there are some theorem preventing formation of singularity into dimensional flow. How would you cope with them? I forgot the name of author.
So the problem is the following: what you have two flows indeed. Let's imagine that you have just a simple situation where the pressure is a constant. In such a case, it turns out that if you consider the velocity profile, which has a negative initially, the profile must be negative. In such a case, you have so this means that you have two flows indeed, and then you have a just I don't know, collision, and this collision provides you appearance of singular behavior.
So,
and in fact, if you look at
it is only in framework of this Prandtl approximation.
Yeah, in the Prandtl equation. But however, if you look at the papers by Ho and Low, you can find something very familiar qualitative arguments. Why they have a formation of singularity on the wall of cylinder, and they not exactly what I am speaking now, but however, I believe that the explanation of his numerics appearance of singularity is connected is nothing more with the slipping flow. So rigid boundary itself produces you appearance of singularity.
Even Hall's experiment, I know, yeah. Mm-hmm.
Yes. And so what's important is the following, that we demonstrated that for the Biscuit-Prandtl equation, appearance of finite time singularity can happen on the wall, and in two-dimensional and three-dimensional. In three-dimensional case, it's very important. It produced not only singular behavior for stress tensor, but for vorticity itself.
No,
And
I think, stop. The presence of flow, this is really important.
yes, yes,
Uh-huh.
very
Okay.
important. In fact, it is the main point of my talk.
Main-
So this means
main
that in
point.
some
Yeah,
sense,
I
the
understand what you mean.
sliping flow in such a case occurs some compressible, but of course incompressible as in the whole region. So divergent V of course equals 0 is not a question, but if you consider the dynamics for tangent component velocity, so parallel to the wall, in such a case you will have the Hopf equation or something like that. So in fact it's an observation, but I believe that it should be very important for understanding why boundary plays two essential role in appearance of singularity in real fluid. I mean, not for Prandtl equation, but for Euler, for instance. So I finish. Thank you very much.
Thank you very much, and it was quite
Thank you.
interesting.
Thank
too.
you. I think we have a
Extremely
couple of minutes for
interesting.
some questions. Please, questions.
Okay. I hope that my talk